Hello everyone, and welcome back to our course on using information theory to analyze complex systems. In this next session, we're going to look at effective network inference. That is, inferring or modeling a network structure which can explain the time series dynamics of a set of variables that we have access to when we don't have access to the network structure itself. So in this session, I want to give you an understanding of different options for network inference from time series data. In particular, we're going to talk about structural network inference, functional network inference, as well as effective network inference. And we'll focus on that latter option, effective network inference. In particular, I want you to understand the complexities and subtleties involved in inferring or modeling network structure in this way. I'll show you how to use JIDT for simple, effective network inference, just looking at pairwise relationships. And we'll talk about more advanced multivariate techniques, which we can do with the measures that we have talked about in our past lectures. We're going to talk about their pros and cons, and I'm going to show you how they can be implemented using these measures and point you to a more advanced toolkit, IDT Excel, that implements those algorithms using JIDT under the hood. The primary reference for this session is a section out of the Bossenmeyer and Company book on introducing transfer entropy that deals specifically with inferring network structure using these kinds of measures. So this first short video of the session considers the theory behind the different ways that we can infer network structure from time series data. So let's focus on the key question that we have here. If we're given only time series data for a set of variables in our system, here for X, for Y1, for A, for Y2, for B, and so on, if we're only given their time series of activity in some multivariate time series of states, but we don't have what the underlying network structure is, how can we go about building a network model that represents the relationship between these variables? Okay. How can we build the network model? We're coming back to that word model that we've hit on a few times in our recent lectures. There are three different well-known options that we can take to address this question. We can look at what we call functional networks at one extreme, structural networks at another, and a hybrid approach that we call effective network inference that will be our focus here. But first, let's define functional and structural network inference before we come to effective network inference. Functional network inference tries to construct undirected networks to represent relationships between the nodes. When we draw a link on a functional network model, all we're really saying is that there is a relationship between the nodes. Typically, we do this using a measure of correlation or straight up mutual information between their activity time series. What's important to recognize here is that the functional network provides no explanation for how the relationship manifests. It simply states that there is a relationship between the variables. So it's a very, very general inference of a relationship. We can look at a very brief example here if we look at our common driver motif where Z drives both X and Y. If we apply a measure of functional network inference here, we're likely to see a relationship between all of the nodes here. It's obvious that we should see a relationship between Z and Y, that we should probably see a relationship between Z and Y and between Z and X. What we need to understand is that X and Y are likely to have some kind of relationship as well because of that common driver effect. So if you apply functional network inference to this kind of motif, that's what you're likely to get. As I say, it's a very general inference of a relationship. It's not terribly specific. Structural network inference, on the other hand, is kind of at the other extreme. It is looking directly at constructing the directed relationships here, so not undirected anymore, but directed, to represent the real physical directed or causal connections in the network. So here in this common driver example that we just looked at, we've got our black arrows representing the real physical directed causal connections here, and that is what structural network inference is trying to unveil. We need to understand that this is generally only possible to do via interventional techniques. This is something that we talked about in our previous lecture on information transfer when we contrasted it with causal effect. We talked about the Pearl interventional view of understanding causality, that we really need to intervene in the network to understand the causal effects. Okay, so that's exactly what we're talking about here. So generally, if we want to talk about the underlying causal structure, it's generally only possible to get to that via interventional techniques, but not directly from large observational multivariate time series sets alone. Under certain circumstances, Pearl shows us when that's possible, but typically we don't have the conditions for that satisfied in multivariate time series that we're looking at. For example, in a multivariate time series of MEG data, we're almost never going to have those conditions satisfied. So there's not much point considering them here. We also need to understand that just having the structural network doesn't tell us about time or experimentally modulated changes in how the variables are interacting. The structure may not be enough for us to understand the system. We can think about this in the context, for example, of the C. elegans worm. We have its brain structure completely mapped out. Does that mean that we completely understand the computation that's taking place there? I'm not sure that we can really say that we do. We can take that analogy further to the human brain. There's a lot of effort going into understanding the connectome. That will get us part way there. It's not going to get us all the way there to understand how to model the computation that's taking place on those networks. Effective network inference is kind of a hybrid between those two approaches that we've just looked at, and it's the approach that we're going to focus on through the rest of this session. Effective network inference seeks to infer directed relationships, like we saw with structural network inference, and indeed to infer the minimal neural circuit model, if we're looking at neural data that is, but otherwise the minimal circuit model which can replicate and indeed explain the time series of the nodes. Okay, so this contrasts to both the structural network inference and the functional network inference. It's got the directed aspects like structure, but we see our keyword model here again. It's not directly trying to get at that structure. It's trying to model a structure that can explain the dynamics. Okay, so it's going much further than functional in particular as well. So we need to understand that it's not structural, but it may be the best that can be done with data alone. If we're trying to infer a structure from data and we really want to infer a structural network, then taking an approach of inferring effective connectivity may be the best that we can do, because as I already said, causality is often impossible when we've just got time series data alone. When we have all of the nodes in the network available, so there's no hidden nodes, when we have enough data, sort of in the limit that we have observed all the possible network configurations, then our effective network inference should be expected to reflect the structural network inference very well. What I think we need to keep in mind, though, is that we shouldn't just look at effective network inference as a poor man's view of structural inference. It has advantages of its own, and I think that's very important to bear in mind here. For example, effective network inference can reflect dynamic changes in the regime of the system. For example, if we measure brain activity during one cognitive task, it may well be that one particular physical brain connection isn't used during that task at all. If we wanted to get at the structural network, we would want to pick that up. If we want to get at the effective network, we shouldn't pick it up during the measurements of that activity because it's not in use at that time. Furthermore, we can think about effective network inference as modeling the computation taking place in the system. This is coming back to that keyword model that was in the original definition of effective network inference that we can find in the Friston article and spawns below. So coming back to that word modeling, what we're trying to do here is to model the computation taking place in the system, revealing emergent computational structure. And you can start to see that the way I'm describing effective network inference here in comparison to the structural inference has a lot in common with the way we described information transfer with respect to causality in our previous session. So it should be no surprise to you that in the short videos coming up, we're going to look at transfer entropy as a measure that we can use in effective network inference here. Before we get to that though, I want to talk a little bit about what we can use effective network inference for. There are lots of different application domains, and there are lots of different particular questions that we can use it to ask. And I just want to take you through a few of those briefly. One of the big areas for effective network inference is in neuroimaging, taking fMRI data, taking MEG data, taking EEG data, and so on, and then inferring or modeling the underlying information network for the system that can give us a neuronal circuit model to explain the dynamics taking place. Okay, there's a lot of reasons why we want to do that in neuroscience, and in particular, we can look at how those networks change with conditional cognitive tasks that we give the person to do. This diagram here is for one particular paper that we've written, modeling a visuomotor tracking task from fMRI data, for example. And indeed, we examined in that research how the effective network changed with the difficulty of the tracking task. Other application areas include financial market data sets, looking at the way equity prices change over time. And there, in particular, we can look at how the network changes over time. When are we seeing stronger interactions among equities than others? Do we see stronger interactions before a market crash or after, or so on? There are lots of different other application areas. For example, network inference is very strong in gene regulatory network research, for example, as well as social media analysis. This is a very hot area for applying transfer entropy to try and infer social network structure from activity alone. We also see this coming up in sport analytics. This picture here is from one paper that we wrote, analysing interaction between RoboCup players in artificial soccer leagues. And there are many, many more applications beyond this. In the next short video, what I'm going to do is to start looking at how transfer entropy can be used to quantitatively give us an algorithm for effective network inference.